discuss set operations and laws of set operations. Now, our starting point is U, the universe, and capital A, capital B, capital C, etc., which are subsets of U. Now, we define several operations involving these sets A, B, C. We define the following: A union B the union of set A and set B is all x, strictly speaking, all x in U such that x belonging to A or x belongs to B. Now, this is intuitively very clear. This only means that given any two sets A and B, I can consider a set which contains all the elements of A and all the elements of B. Needless to say that it will contain the elements which are both in A and B, and this bigger set is denoted by A union B. This symbol is the symbol of union of two sets. So, this is an operation on sets. The next operation that we define is called the intersection of two sets. We write intersection as this and B. So, this symbol is called the intersection, and this is the set of all x belonging to U such that x belongs to A and x belongs to B. At this point, I would like to mention a diagrammatic representation of sets proposed by John Venn who lived between 1834 to 1923. The diagrammatic representation that he proposed is famous as Venn diagrams. The idea behind Venn diagram is very simple. It just says that when we are considering the universe U, we will write a rectangle or draw a rectangle and call that U our universal set, and the subsets or the sets of the universal sets that we discuss within this framework, which are of course subsets of U. So, these sets, that is A, B, C and all the others, will be drawn as circles inside U, where the interior of the circles may be shaded. When I write this, this means that A consists of the elements that are within this circle. Now, suppose we take another set B. In general, it will have some common area shared with the circle corresponding to A. Let us call it B. Let us go to the next page and draw this situation one more time. So, here we have the universal set U, or simply the universe. I am representing the set A by the inner portion of a circle and B the inner portion of another circle. If we want to know the set A union B, this will consist of the shaded area which consists of the region that is covered by A and the region covered by B. So, this whole shaded area is A union B. Again we take A and B. If we consider only the region that is within the interior of the circle corresponding to A and the interior of the circle corresponding to B, then we get the set A intersection B. Now, this pictorially gives us the sets A union B and A intersection B, and these diagrams are very useful in getting an intuitive feeling of operations on sets. The next operation that we discuss is called symmetric difference. Now, let us check the definition of symmetric difference. This is the third sub part of the first definition that we have started. Symmetric difference is denoted by delta. So, again we have two sets and I am writing A delta B. This is the symmetric difference of the set A and the set B. And this consists of all the elements in U such that X belongs to A union B and X does not belong to A intersection B. Now, let us take the help of the Venn diagram to understand this operation. Suppose these are my sets A and B. So, I am looking for the region which is inside A union B and which is outside A intersection B. Let us recall what is A union B and what is A intersection B. A union B is the shaded region that covers the whole of A and B, and A intersection B is this part. So, if I superimpose these two diagrams, then we will find that this part is A intersection B, and therefore, I have to cut this portion out. I do not want elements there, and all the other elements will be in the symmetric difference. Therefore, the symmetric difference is a set which can be represented by the Venn diagram as the shaded region within A union B. So, this is whole of A union B, leaving aside the portion A intersection B. There are two more operations that I would like to discuss over here. One is A set minus B. A set minus B. This is the set of all x such that x belongs to A and x does not belong to B. If we look at the Venn diagram corresponding to this operation, then we see something like this. Again we have the universal set and we are taking two sets A and B within that universal set, and I want the elements which are in A, but not in B. Therefore, I shade the portion of A which is outside A intersection B. This shaded region corresponds to A set minus B, or simply A minus B. Now, if we inverted this situation and if we had taken B minus A, we would have gotten x belongs to U and x belongs to B and x does not belong to A. Now, in Venn diagram, that means the region which is inside B, but not in A intersection B. So, if you have A here and B here, this is the region corresponding to B minus A. This is B, I am sorry, this is B minus A. Thus, we can combine these two things and get a different description of symmetric difference of A and B. The symmetric difference of A and B can also be thought of as A set minus B union B set minus A. We have to remember this. Now, let us look at some examples. Suppose our universal set is integers from 1 to 10, and let us consider the sets A, B, C as then A union B is 1, 2, 3, 4, 5, 6 and 7. So, that is the integers which are both in A and B. If we want to find out A intersection B, that will take only the integers which are common to both A and B, and we see that 3 is common to both A and B, 4 is both common to A and B, and same is 5. Therefore, it will be 3, 4 and 5. Now, if we take B intersection C, B intersection C is only 7, because we see that this 7 is the only integer which is common to both B and C. And then if we consider A intersection C, we see that A is 1, 2, 3, 4, 5 and C is 7, 8, 9. Therefore, A intersection C does not have any element. So, it is the empty set phi. We have defined empty set in the last lecture, and here we see an example of the empty set. Now, let us consider the symmetric difference between A and B. So, in order to do that, I have to find out elements which are in A, but not in B, and the elements which are in B and not in A. We can as well use the relation that we have obtained over here, that is A minus B union B minus A. If I do that, then first let us consider A minus B. So, let us compare A and B. 1 is in A, but not in B, 2 is in A, but not in B, but 3, 4, 5 all are in A, all are in B. Therefore, from A minus B is going to be only 1 and 2 union. Now, we see that 3, 4 and 5 are common to both A and B, and in B we have 2 more terms or 2 more elements 6 and 7, which are not in A. Therefore, those elements will appear in B minus A, and thus we have the set 1 2 union set 6 7, and taking the union we have 1 2 6 7. So, this is a symmetric difference between A and B. One more operation that we need to consider is said to be the complement. So, we have a set A, which is of course a subset of the universal set. Complement of A is denoted by A bar or A overline and defined as complement of A is a set consisting of all x belonging to U such that x is not in A, or in other words, by using the operations that we have defined already, the complement of A is U set minus A, that is the elements in U which are not in A. Now, we will consider the laws of set theory. I will note down several laws here, many of them are quite intuitive and extremely clear. So, I will not give the proofs in general, but I will give sketches of proofs as we go on describing these laws. Only one or two laws we will check in details. Now, the first one says that A complement is equal to A. This is called the law of double complement. It is not difficult to prove this, because we can always say that suppose I have got an element x which is inside A complement of complement. This implies that x is not in A complement. Now, if x is not in A complement, this automatically implies that x is inside A. The reason is that A complement consists of exactly those elements which are not in A. So, if something is not in A, then it is of course in A. Therefore, we see that any element in A complement is going to be in A. Therefore, A complement is a subset of A. On the other hand, if I have an x inside A, this will mean that x definitely is not inside A complement, but from the definition of complement I can take again a complement, because x is not in A complement, and I can consider A complement as a set with which I am starting. Then I take complement of that, and then x has to be inside complement of A complement, and therefore, A must be a subset of A complement, and combining these two results, we see that A complement is equal to A, which is called the law of double complement. The next result is the De Morgan's law, which states that A union B complement is equal to A complement intersection B complement, and A intersection B complement equal to A complement union B complement. This is called De Morgan's law. Now, De Morgan's law needs a proof. So, let us start with the proof of De Morgan's law. Let us write De Morgan's law again. It states that A union B complement is equal to A complement intersection B complement, and A intersection B complement equal to A complement union B complement. First, we prove this part. In order to prove this equality, we start by considering an element x inside A union B complement, which implies that x is not in A union B. Now, let us draw a small Venn diagram over here and see what happens. So, here we have got, of course, this is the universal set U. Here we have got A and B, and here somebody tells me that x is in A union B complement. I know that A union B covers the interiors of the circles corresponding to A and B. Therefore, A intersection B definitely is a region outside A union B. So, this shaded region is A union B complement. So, I am saying that A x belongs to A union B complement implies that x does not belong to A union B. But what does it mean? It means that x cannot be inside A, neither can be x inside B. Therefore, this means that x is not in A and x is not in B. Now, we know that if somebody tells me that x is not in A, this means definitely x is inside A complement, and x not in B means definitely x is inside B complement. Now, this means that x is inside A complement intersection B complement, because this is the definition of intersection, that if I have an element which is inside, let us say, set C and also inside set D, then that element is inside C intersection D, and here those two sets are A complement and B complement. Therefore, x belongs to A complement and x belongs to B complement, means x belongs to A complement intersection B complement. Now, we have proved here that x belonging to A complement union, x belonging to A union B complement implies x belongs to A complement union, x belongs to A complement intersection B complement. Therefore, we can say that A union B complement is a subset of A complement intersection B complement. Let us write this equation as the equation 1. Next, we start from the last line of the previous chain of arguments. So, we start from the point that x is an element of A complement intersection B complement. Suppose this happens, then this implies that x is an element of A complement and x is an element of B complement. This means x is not in A and x is not in B. Now, we again refer back to the Venn diagram that I have drawn a while back. And we see that if I have a scenario where x is not in A and x not in B, that means x will be in the region outside, exactly outside A union B. Therefore, I can safely say that x does not belong to A union B, which means that x belongs to A union B complement. Therefore, we can write that A complement intersection B complement is a subset of A union B complement. Let us denote this by 2. Now, here we see that we are considering two sets, that one is A union B complement and the other is A complement intersection B complement, and we have proved that the set in the left hand side is a subset of the set in the right hand side, and the right hand side is a subset of the set left hand side because of these two subset equality relations, and therefore, we can safely say that these two sets are equal, and this is the first part of De Morgan's theorem. Now, let us try to prove the second part of the De Morgan's theorem. Here our starting point is x is inside A intersection B complement. Now, this means that x is not in A intersection B. Now, x is not in A intersection B means that x is not in A or x not in B. Let us see that Venn diagram corresponding to this situation. This is A, this is B. So, let us write the sets A, B, and this is A intersection B. Now, I am told that x is not in A intersection B. So, that means x is not here. This means that x cannot be both in A and B, because if x is in A and B both, then it is inside A intersection B. So, that means either one is correct, either x is not in A and in B, or x is in B, but not in A, or x is in neither. Therefore, x can be anywhere over here, and that is expressed by this, but this means that x belongs to A complement or x belongs to B complement, which means that x belongs to A complement union B complement. Therefore, like before, we can write that A intersection B complement is a subset of A complement union B complement. Let us write this as 3. We can start again from the last line, taking x to be belonging to A complement union B complement. This means that x belongs to A complement or x belongs to B complement, which in turn means that x is not in A or x not in B, which in turn means x not in A intersection B, which in turn means x belongs to A intersection B complement, which gives us A complement union B complement is a subset of A intersection B whole complement. Call it 4. Combining 3 and 4, we have A intersection B complement equal to A complement union B complement. This completes the proof of De Morgan's law. Now, let us quickly list all the other laws which are used very frequently. A union B equal to B union A, and A intersection B equal to B intersection A. This is called commutative law. For A union B union C is equal to A union B union C, and A intersection B intersection C is equal to A intersection B intersection C. These together is called associative law. Five, A union B intersection C is equal to A union B intersection A union C, and A intersection B union C is equal to A intersection B union A intersection C. These two together is called distributive law. Six. Now, A union A is equal to A, and A intersection A is equal to A. This is the idempotent law. Seven, A union phi equal to A, that is of course, if I take union of A to the element which has no to the set which has no element, then the result is A. Similarly, if I take A and take the intersection with the universe, then also I will get A. This is called identity law. A union A complement is U and A intersection A complement is phi. This is called inverse law. Lastly, we end today's lecture by a law which is called absorption law and which is useful very often, which goes like this: A union A intersection B is A and A intersection A union B is also A. This is called absorption law. These laws more or less covers the most important properties of set operations which are used to manipulate sets. We have proved some initial laws and later on we have given a complete proof of De Morgan's law, which is not very easy to see, and the rest of the other laws are quite intuitive and I leave it as exercise for the participants. We stop the lecture today here. Thank you.